So the setup here involves a bunch of magnetic fields essentially. So we have the main magnet, which exerts the external constant field on the body. It's a superconducting helium-cooled magnet, which ensures that the field remains as uniform and constant as possible. Then we also have radio frequency coils, which are capable of both transmitting and receiving radio frequency signals. We also have magnetic field gradients, which are gradients that are applied in 3 different directions and which help us localize the MRI signal. Now, all these things are controlled by the computer system. Except the main magnet. So the RF coils and the gradient coils are controlled by the computer system. So that's the basic setup of the MRI. Now let's see how this setup produces the image that we're talking about. So as I was saying, the main magnet produces a strong static field B naught. The RF coils excite protons by producing a radio frequency signal. They also receive the radio frequency signal, which is then emitted by those protons. Magnetic field gradients localize the signal, as I said, and the computer system converts the signal to image, participates in archiving, etc. So what happens? The patient is put in the field B naught, which is exerted by the main magnet. So this field B naught can have values of either 1.5 Tesla or 3 Tesla. And you should know that this is a very, very strong magnetic field, several times greater than the magnetic field of the Earth. So the patient is put into this magnetic field, which is created by the main magnet. And all the protons in the patient's body, which are tiny little magnets, will have a reaction in response to this magnetic field. So they will either align with the magnetic field or they will align against the magnetic field. And you should know that more protons align with the field than against the field. And we'll discuss why in just a second. So you might be confused at this point because if you've ever played with magnets in your life, you'll know that in the presence of another magnet, they only ever align in the same direction. So why is it that these magnets can either align in one direction or the opposite direction? And the reason for that is that the magnets we're talking about here are quantum magnets. So we have to expect them to behave in ways that are different from classical magnets. That's kind of a hand-wavy explanation, but we'll talk about what it means for magnets to align in 2 different directions in just a second. But the answer is that it's a quantum magnet and there are quantum effects at play, which cause the alignment of the field to be one or the other. Okay, so if you take a look at the diagram on the left-hand side, you'll see there's a magnet, which is a proton, which is aligned a certain way, and a proton, which is aligned in the opposite way. And when the magnetic field is applied, basically one set of protons aligns with the field where they have lower energy, and another set of protons aligns against the field, and then they have a higher amount of energy, which makes sense, right? Because imagine if you're in a river, and the current is flowing very strongly. It's easier for you to flow along with the current, whereas if you're going against the current, you need a greater amount of energy. So in the same way, the protons which are aligning with the field have a lower amount of energy, and the protons which are aligning against the field have a higher amount of energy. Now, this amount of energy is given by the formula h mu, where h is Planck's constant, which we saw again earlier, and mu is the frequency. And it has a certain number, which is related to the magnetic field we've applied, directly proportional to the magnetic field that we've applied. So if the direction of the magnetic field changes, a different alignment occurs. Now, so what we've done is we've applied a certain magnetic field and the protons have aligned themselves in a certain way. Some have higher energy, some have lower energy. Now what we do is we flip the direction of the field. What's going to happen is the protons align in a different way. A whole bunch of protons will flip, a whole bunch of protons will, So what happens then is that the energy of the protons is changing. Some protons lose energy and some gain energy when the alignment changes. So now if the magnetic field starts to oscillate, by oscillate, we mean, so sorry, that's my Telegram chat again. Let me just open that up. Yeah, okay. So what we mean by oscillate is that the magnetic field is applied in one direction, which means the north to south is in a certain direction. Then suddenly it's flipped. The south is in the opposite direction and the north is in the other direction. And by oscillate, we mean that it starts going up and down really rapidly at a certain frequency. So when that happens, the protons also start changing from the high to the low energy state quite frequently. Now, this frequency at which they start changing to a different magnetic state is given by the formula above. And this oscillating magnetic field is equivalent to an electromagnetic radiation of similar frequency. So oscillating magnetic field is equivalent to an electromagnetic radiation of similar frequency. So what happens is there are more low energy protons. That's a given in any natural system. There's always things which are at a lower energy compared to things which are at a higher energy. So when the field oscillates, there's a net gain in energy that happens. So because the lower energy is going to the higher energy, so there's more higher energy protons later, which means that the system as a whole has more energy. So this gain in energy is from the absorption of the radiation energy. So this energy will later be radiated as a signal. And when B naught is 1 Tesla, the frequency mu of the radiation that's emitted is 42.6 megahertz, which is in the radio frequency region. So let me just try to explain this. We've had a lot of formulas. We've had a lot of numbers thrown in. So let's just try to discuss what happens. Essentially, if the magnetic field starts to oscillate at a certain energy, the protons can change from the high to the low energy state, and there's a net gain in energy. That frequency of oscillation is given by the formula that I've written on the top. Now, yeah. And the interesting thing is this frequency of oscillation can be used, an oscillating magnetic field can also be used, you can apply an electromagnetic radiation with the same frequency, and they're both equivalent to each other. So which electromagnetic radiation are we applying here? It's the radio frequency. And you can see here that when the external field that is applied is 1 Tesla, the frequency mu will have the value 42.6 megahertz, which is in the radio frequency region. So this is all to answer the question, why are we applying radio frequency to the protons and not some other kind of frequency? The answer is we need to make the protons oscillate up and down in their low and high energy state. And in order to do that, because the value of the external magnetic field is around 1 Tesla, 1.5 Tesla, 3 Tesla, the oscillating magnetic field that we need to apply will come from an electromagnetic radiation in the radio frequency range. I hope everyone's familiar with the electromagnetic spectrum, but yeah. So eventually what happens is this oscillation causes the protons to go to a high energy state. Once the oscillation of the magnetic field stops, the protons will lose the energy they gained or relax. So this relaxation gives us useful clinical information. So that's essentially what happens, and we'll go through this in detail and find out what happens. So we were discussing why do some protons align against the field, because that doesn't happen in classical magnets. So let's discuss why that happens in terms of proton alignment. So a normal magnet would lie exactly along the field. A normal magnet is the one I put on the left-hand side. The protons are ruled by quantum mechanics. They all align at an angle to the field. Okay. So we've gone through a lot of concepts right now, and we're halfway through the webinar. If there's any questions at this point, you can discuss those with me. If not, I'm going to take a 5-minute break, just so we have time to go through our notes and see, are there any specific questions that you want to ask at this point? Any doubts that you have? We'll just take a 5-minute break, and then after that, we'll go straight into the rest of the theory. So I'll just keep my mic and my video off for 5 minutes, and then I'll continue with the presentation. Or if everybody's good to go, if you don't need a break to look at your notes, you can put a yes in the chat box, and then I can keep going. Because it's quite a theory-heavy subject, I want to give people some time to sort of absorb what they've heard in the last 30 minutes. Okay, so we'll take a break. I'll just pause my mic for just 5 minutes, and then I'll continue with the rest of the theory. So we started exactly at 5, and break will end at 5:30. So if you want to go get yourself a cup of coffee or a mug of tea, or just stand up for a few minutes, please go for it. Yeah. I'll get a cup of coffee myself. Okay, so hopefully that was enough of a break for everybody. So let's continue on. Okay, so next we're going to discuss a concept which is known as llama precession. All right, so we're going to talk about when the proton is spinning. So the proton is spinning on its own axis like a tiny little planet. The angular momentum, spin angular momentum points along, if you imagine the proton is spinning around an axis, the spin angular momentum points in that direction, along the direction of the axis. So when an external magnetic field is applied, then a certain phenomenon takes place. So the proton spins on its own axis. The proton also precesses. So you can see a gyroscope precessing on the left-hand side. Precession is the motion that you see here. So this gyroscope is like a spinning top. It's spinning like this, but the top of the gyroscope is also turning along the point of a cone. So precession causes the magnetic dipole moment of the proton to travel along the surface of a cone.